Dear students, today we are going to conduct open circuit and load characteristics of separately excited DC generator and to calculate the critical resistance and critical speed. So the aim of this experiment is to obtain open circuit and load characteristics of separately excited DC shunt generator and also to find the critical resistance and the corresponding critical speed. So this is the circuit diagram of the open circuit test and load characteristics of separately excited DC shunt generator. Right. So here you see, so this is your supply, positive and negative terminal. You have a DPST switch, then you have a fuse, then you have a 3-point starter. So the 3 points are line, field, and armature. Right. So then you have the generator which is coupled to your motor. So the generator field is excited separately from the common supply. So this DC supply is common for the motor as well as the field winding of your generator. Again, the generator is separately excited, right, from the supply. So it is called as separately excited DC shunt motor. So this is the nameplate detail of the motor and generator. Yes, so this is your nameplate detail which I have written in your manual, right? So the power rating in kilowatt is 3.7 kilowatt and in HP is 5 HP, voltage is 230, amps is 19 amps for your DC shunt motor, and the speed, rated speed is 1500 RPM. This is the value for your DC generator. So the kilowatt is 2.2 kilowatt. So your voltage is 220 volt and your current is 10 ampere and your speed, rated speed is 1500 RPM. So the nameplate details of your motor and generator are written here, right? So and then the fuse rating calculation. So the fuse rating is 125 percentage of rated current for your load test, right? So it is 1.25 into rated current. So 1.25 into rated current is 19 amperes for your motor. So it is 23.75 amperes, approximately 24 amperes. Right. So now we will see the circuit connection. So from your positive terminal of your DC supply, so a DPST switch is connected, and from DPST switch the wire goes to your L line terminal of 3-point starter. From the field terminal of 3-point starter, a variable rheostat whose rating is 300 ohms bar 1.4 ampere. This is called as field rheostat. So this the wire from your field terminal of 3-point starter is given to the input of your rheostat. The output of the rheostat is connected to your F1, right? So then your F2 terminal is connected to the A2 terminal. So F2 is field winding, right? So and A2 is armature winding. So your field winding and armature winding are short circuited. So then from 3-point starter armature, so your armature of the motor is connected, right? And then here the short circuited F2 A2 is connected to your negative terminal, right? So and then from the from the positive terminal, right, of your DC supply, so the rheostat is connected here, right? So the rheostat of your motor, the field rheostat of your motor is in minimum position, whereas the field rheostat of your generator is in maximum position, right? So from positive terminal of your DC supply, so the input of your rheostat is connected. From the output, field winding 1 of your generator is connected. Then the field winding 2 of your generator is connected to the positive terminal of the ammeter, and from negative terminal of the ammeter the common negative is connected here, right? So the negative terminal of the ammeter is connected to the negative terminal of the DC supply. and then the armature 1 of your generator is connected to the voltmeter positive terminal, and armature 2 terminal of your armature for generator is connected to the negative terminal of your voltmeter. So the load is connected parallel to your voltmeter, and to measure the load current, and ammeter is connected in series with your load. So from positive terminal, so you have a DPST switch, and then you have a positive terminal of your ammeter, negative terminal is connected to load, and again the next terminal of your load is connected to the DPST switch, and from DPST switch your negative terminal of the voltmeter is connected. So this is your experimental setup for conducting open circuit test and load characteristics on a DC generator. So the first is your 300 ohms 1.4 ampere. The second rheostat is your 700 ohm 1.2 ampere. So this is your meter to measure the field current, right? So the field current is very less. So we are using a 0 to 2 ampere meter, right? So then this is your SPST switch, single pole single throw switch. So you can able to connect that is you can able to close your switch once and open your switch once. So then to measure your load voltage or terminal voltage, so here you have the voltmeter. So here the voltmeter range is 0 to 300 volt, right? And here ammeter is 0 to 10 ampere. So here we are using 0 to 10 ampere because the rated current of the DC shunt generator is 10 ampere. And this is your loading rheostat, right? This is the loading arrangement for a DC shunt motor. So here the power, right, is 3 kilowatt, and your voltage is 230 volt. So the amperes is 13 amperes, and it is a single phase rheostat, right? So this is your loading arrangement. So let me show you how to connect your meters, rheostat meters and switches. So first from positive terminal, so the wire is connected to your L, right? So then from field terminal of your starter, so the wire is given to your 300 ohm 1.4 ampere rheostated input. The slider is near the input, so it is in the minimum position. So from the output of your rheostat, so it is connected to the field winding, terminal 1 of your field winding. From terminal 2 of your field winding, so this field winding is the motor field winding. From terminal 2 of the field winding, it is given to your A2, right? So that means your field winding and your armature are shorted together. F2 and A2 are shorted together. So from A2, you are giving it to the negative terminal of the supply, right? So then the A terminal of the DC starter is connected to the armature terminal of your DC shunt motor. So then we have to connect the DC shunt generator. So here from positive terminal you are going to connect your SPST switch. From positive terminal you are going to connect your SPST switch input, and from output of your SPST switch we are giving it to the rheostat input, right? So here from the output of your rheostat we are going to give it to the field winding. So the both the rheostats are used for varying the field current of motor and generator respectively. So here the slider is near the output, so your resistance is said to be in the maximum resistance position. So the field rheostat of motor is in minimum position, whereas the field rheostat of the generator is in maximum position, right? So then from your output of your rheostat we are connecting it to the field winding of generator. Then the field terminal F2 of the generator is connected to your ammeter positive. Then ammeter negative is connected to the common terminal negative, right? DC supply negative terminal. So then, so here A1 terminal is connected to your voltmeter. This is your A1 terminal. So this wire, blue color wire, is connected to your positive terminal. So from negative terminal we are connecting it to your A2. From negative terminal we are connecting it to the A2. Then we are going to connect the load, right? So the positive and negative terminal of the loads are connected to positive terminal of your negative terminal of your ammeter, and then negative terminal of your voltmeter, right? So the positive terminal of the load is connected to ammeter negative, the negative terminal of load is connected to voltmeter negative, and ammeter positive and voltmeter positive are connected together. Now we are going to conduct the experiment. So the main supply is turned on, right? So then we are going to turn on the MCB so that the supply is given to your motor generator set. By varying the 3-point starter, we are going to start the motor generator set. So the 3-point starter should be varied slowly so that you can able to start your motor generator set. Then we are going to measure the speed of the motor generator set. So the rated speed of both the motor and generator is 1500 rpm. Now it is reading at 1324 rpm. By varying the field rheostat of the DC motor, we are going to set the speed of the motor generator set at rated speed, that is 1500 rpm. So now we are again going to measure the speed of the motor generator. So still it is reading at 1512, 510, right? So now we can reduce the rheostat a little bit so that the rated speed is 1500. So now we are again going to measure whether it is 1500 or not. So now it is 1492. So here we are going to slightly vary. Yes, so now it is set at rated speed 1500 rpm. Yes, now it is 1500 rpm. So now you look at the voltmeter reading, right? So we have not closed the switch, right? So before closing the switch, you can able to read 10 to 12 volt. So this voltage is due to residual magnetism. So residual magnetism is the magnetism experienced by your generator, right? So this is due to frequent magnetization and demagnetization, right? So before giving a current and exciting the windings to act as a electromagnet, so there is a residual magnetism, right? So you are getting this voltage before closing this SPST switch. So you have to note down this voltage due to residual magnetism, which is called as a residual voltage. So now we are going to close this switch, SPST switch. So your voltage is now 110 volt, right? So we are going to see the corresponding current for 110 volt. So here the corresponding current is 0.04 is 0.1. So here it is connected to 2, right? Yes, here it is connected to 2. So here it is 0.05, yes, 0.02. So we have to multiply it by 2. So 0.02 into 2 will give you 0.04. So I have tabulated the readings. So the armature voltage is 110 volt and the field current is 0.02 into 2 is 0.04 ampere. So now we are going to vary the field rheostat of your generator, right? So field rheostat of your generator is varied gradually. Field rheostat is varied gradually, so the position is changed from minimum position maximum position. Right now you can able to see your voltage. So now the voltage is increased to 140, right? And the current, you see, 0.15. So 0.15 into 2 is 3. So now again we are changing the rheostat position, right? So you look at your voltmeter, so it is changing to 160. So it is 150. It is 150 now. It is increased to 10 volts from 140 to 150. So now your current is also increased from 0.15 to 0.17, right? So then again you have to vary the field rheostat of your generator. So now so you have to vary the rheostat, and you have to set the voltage up to 220, right? So then your current here is 0.32, so which is 0.64, right? So now we are going to tabulate the readings, right? So reading number 1, 2, 3 and 4. So the reading number 2 is 140 volt, it is 150 volt, the last one up to 220 volt. So here 0.15 into 2, 0.17 into 2 up to 0.32 into 2, right? So this is your tabulated readings, right? So starting from 110 volt, we are gradually varying the rheostat, field rheostat from the maximum position towards the minimum position, and then we are noting down the voltage as well as the corresponding field current, right? So this is called as open circuit test, and with this test we are going to draw the magnetization curve, right, or open circuit curve for your DC shunt generator. So then we are going to perform the load test. We are going to load the DC motor generator set. So for that we are going to switch on the mains of your rheostat load. Then we are going to vary your load, right? So first I am going to turn on 0.5 amperes, right? So then we are going to see the voltage, right? Then we are going to see the current. So this voltage is called as load voltage, and this current is called as load current. So here the loading should be done up to 10 ampere. So we have to take readings less than 10 ampere, because 10 amperes is the rated current of your generator. So now you see your voltmeter. So the load is now 1 ampere. The voltage is same 220 volt, but your current is increased from 0.5 to 1 ampere. You loaded your motor with 2 amperes. So the voltage is reducing, right? And then the current is increasing to 2 amperes. So then the load is increased from 2 amperes to 3 amperes, which is indicated by your ammeter, and then the corresponding voltage we have to note down, right? So similarly you have to keep on increasing your load. So the load current is increased from 3 to 4, 4 to 5, 5 to 6, etc., right? So you should not increase your load current beyond 10 amperes. So you have to take readings within 10 amperes, because 10 amperes is the rated current of your generator. So in load test we are going to note down the voltage and current, and we are going to write it in the tabular column. So the load test readings are tabulated here. So this is the first load we have applied, so 0.5 amperes. So the terminal voltage is 220 volt. The corresponding field current we have to measure, that is 0.32 into 2.64 amperes. So then we have to add the two values, right? So that is 0.32 into 2, 0.64 plus 0.5. So then we are increasing the load. So now it is 1 ampere. So the corresponding voltage is 220 and the corresponding field current is 0.3 into 2. So we are going to add these two values, it is 1.6. And then the load is increased to 2 amperes, the corresponding voltage is 220, and then the corresponding field current is 0.28 into 2. So 2 plus 0.56 will give you 2.56. And then the terminal voltage is now 200 after loading your shunt generator for 3 amperes. Then the field current is 0.27 into 2. It is 3 plus 0.54 is 3.54. So now we have to calculate your generated voltage, right? EG, generated EMF, is equal to terminal voltage plus IA RA, where RA is the armature resistance. So the armature resistance of your DC shunt generator is measured across its terminal A1, A2 with the help of the multimeter. So this is your armature resistance, which is varying at 1.3 and 1.4. Right. So let us take this armature resistance as 1.4. So here the generated EMF is calculated like this. So generated EMF is equal to terminal voltage plus the product of armature current into your armature resistance. For first reading, so your terminal voltage is 220 plus your armature current is 1.14 into your armature resistance is 1.4. So our second reading it is 220 plus armature current is 1.6 and your armature resistance is 1.4. And for third reading your terminal voltage is 210 plus your armature resistance is 2.56 into armature current is 2.56 into armature resistance is 1.4, and your generated voltage for your fourth reading is 200 is your terminal voltage plus 3.54 is your armature current into 1.4 is your armature resistance. So with the help of OCC data, we are going to plot this open circuit characteristics, right? So you have a field current versus your armature voltage, right, from this tabular column. So we have to plot 0.04 ampere for 110 volt and 0.3 amperes for 140 volt. Similarly, 0.64 amperes for 220 volts, and then we will get this open circuit characteristics curve for your DC shunt generator. Right. So here the magnetization curve is increasing from a minimum value, so it keep on increasing, and at a particular point it is saturating, right? So this is your open circuit characteristics curve, and this is your load circuit characteristics curve. So you have one x-axis, that is load current, and two y-axis, terminal voltage and generated voltage. Terminal voltage is Vt and generated voltage is Eg. Right. So this AD dotted line is the constant value or maximum value, right? And you see the if the load current keep on increasing, then your internal characteristics as well as your external characteristics is dropping, right? So you have two different drops. One is armature reaction drop, right, and then another one is ohmic drop.